This week we're going to focus on using regression methods in Matlab. The first question is, what is a regression? Up until now, at least the way we've been using Matlab, we had some function defined, and we could put in some independent variable, we could put into the function, and we would get out our dependent variables. So we might have had a definition for the position of our rocket. At all points in time, we can put in a vector of time, and we're going to get out our dependent variables, which is the height. What we're doing with regression is going in slightly the opposite direction. We're going to have measurements of our independent variables and measures of our dependent variables. And what we're trying to do is figure out what the function was that relates our independent variable, or independent variables, to our dependent variable. What we have to consider is what's the function that we want to fit to our data set, to our independent measurements and our dependent measurements. Well, that's going to depend on two things. Either we have kind of an underlying theory of how our dependent variables should relate to our independent variables, and that's what we'll look at in our first example. Or we might need to just visually see what's the relationship look like between our dependent variables and our independent variables, and then see what curve is going to best fit that. But either way, we have to come up with either a test function or the function defined by theory, and then use Matlab to fit it. So the basic syntax we're going to use here, we are going to use the fit function in Matlab, although there are other methods for doing fits that we're not going to cover in this class. So the first thing we have to define is our fit type. And there's two different ways we're going to be able to do this. We can either define our own fit type, where we come up with some coefficients that Matlab is going to find for us, and how they relate to our independent variable x. These examples are going to be having only one independent variable and one dependent variable, although you could have multiple independent variables and multiple dependent variables in general when you're looking at regression. Right, so we're going to define our fit type with the fit type command. And in this example, I'm saving it into the variable ft, but you can call it whatever you want. And then the next line, we're actually doing the fit. We're actually doing the regression. So we need to use this fit command, and then we put in our vector of independent variables, and it has to be a column vector for the fit command. And then the vector of dependent variables, again, has to be a column vector. And then the third argument is ft, or that's the fit type that we previously defined. And what we're going to get out are potentially three outputs here. The first is what I'm calling big F here. That is the actual function. So that's going to be the coefficients or the unknowns that Matlab determined best fit our function. The second output is going to be what I'm calling GOF, and that's going to be the goodness of fit, which I'll talk about in a second. And the third is going to be output, and that's going to give us some additional information of how Matlab ran this regression. Now, the goodness of fit, as the name implies, tells you how good of a fit that the curve or the function we chose fits our data. Now, we're going to get a couple of different values out of this. For this class, we're just going to be looking at the R squared value to see how well does our test function fit our data. And in general, this is going to be between a value of 0 and 1, with 0 meaning it doesn't fit our data very well, and 1 means that it fits our data perfectly. So generally, the larger our R squared value is, the better our fit is. There's a lot more detail to this, but we're only going to kind of scratch the surface in this class to what this R squared value means. Now, what's Matlab actually doing in this fit? How is it choosing the variables? Well, I'll talk about that in a little bit when we see the first example here. It can be fairly complicated how it's doing it, but I'll try to boil it down when we get to the example. But what's the point of the regression? Well, there's a couple things we can use this regression for. We only took a limited number of data points in our experiment or in our observation, and what the regression lets us do is it's one method to kind of fill in the gaps between data points that we actually measured. So if we measured something at 5 seconds and measured it again at 10 seconds, we don't have data for what was happening at 7 seconds. But if we run a regression through and the curve we fit to our data fits pretty well, we can make kind of an educated guess as to what was happening at 7 seconds, at 8 seconds, even though we didn't actually measure that during our experiment. Making estimates between data points that we did actually measure is called interpolation. And we'll talk about more interpolation methods in a couple of weeks as well. Now, if we try to use our data set and we tried to predict what happened outside, so maybe we only took data at 5 seconds, 10 seconds, and then every 5 seconds up to a minute, and we want to try to figure out, well, what happened at 80 seconds? This would be what we call an extrapolation. We're trying to predict what happened outside of our collected data set. And for the most part, we don't want to be doing extrapolation because we don't know what happened outside of the bounds of what we measure. So we're going to limit our study to interpolation for the most part in this class. Now we can use this f function to get the value at these interpolated values between, say, times that we measured. And we can use it just like we've used other functions in the past. So if f is the function, if we have f of 4, for example, that will tell us, according to our regression, what should the value be at 4. So 4 seconds or x equals 4, it's going to give us that value. So let's see an example of how we can use this regression. I'll explain a little bit more of what it's doing during that. All right, so going into Matlab, what I'm going to do here is I have some data already, and I'm going to load it in. It's in a mat file. So I'm going to use L04_spring and load that into my workspace. All right, so we see it loads into the workspace here, and I have this variable f and this variable x. All right, and what these are is these are measurements of a linear spring. So we pulled the spring to these different deformations, that's what's stored in x, and we measured what the force in the spring was at each of those. So if we plot it, we can see a little bit nicer what's happening here. I'll plot it as these discrete points. And let me label so we know what's going on. In this case, my x is going to be the deformation, measured in meters for this experiment. And the y-axis is the force in the spring. And that is measured in newtons for this. And I'll turn on the grid. And if we make this look a little bit bigger, all right, so here we go. So we measured every 1 centimeter what the force in the spring was as we pulled it along. So in this example, the point of doing the regression here is we're going to be able to figure out, or at least estimate, what the spring constant is for this spring. Now we know that for a linear spring, it's going to obey Hooke's law. If you remember back from physics, Hooke's law was F equals k times x. So the force in the spring was our spring constant k times the deformation in the spring, or how much the spring stretched from its equilibrium position. Now, since we have an underlying theory of how a spring should work, F equals k times x, if we look at the data that we have here, our x-axis, our independent measurement, is the deformation. Our dependent measurement is the force. So the underlying theory tells us that there should be a linear relationship between the force in the spring and the deformation. And specifically, if we multiply the deformation times that slope k, we should be able to get force. If we look visually of what we have on here at the data, it's more or less looks like it goes along a straight line, but whenever we run an experiment, we can't collect the data perfectly. There's going to be errors in either the independent measurement we're taking or the dependent measurement we're taking, so it's not going to be along a perfect line. So what we're going to do is run a regression, and we're going to see what line best fits our data. So what we can do is I want to define my fit type. In this case, the underlying theory says that it's going to be k, some constant k times x. What we don't know now is k, and that's what we're going to be trying to figure out. What's k? So when I do fit type, I know I'm looking for k, and x, Matlab is going to interpret as my independent variable here. Okay, so I want to define my fit type, and now I want to get out of these values, this f, the GOF, and output, using the fit command, and I have my independent variable x, which has to be a column vector, so I do need to use a transpose here so it's in the correct direction, F and FT. And let me run just this so we can see what this output gives us. Now we're not going to worry about for now that it's talking about start points. That's not going to affect what we're trying to do at the moment. Alright, so let's look at the three outputs we got. So first the F. What did it determine the best fit for our model was? So if we look here, we said that our model should be F equals K times X. And we know that from Hooke's law. That's what we expect the relationship to be. So what we see here is that it came up with our K value. The best K value to use to fit our data was 64.34, and that would be measured in newtons per meter. And we can get our coefficients out. In this case, we only have one. We have K. I can do F dot K, and that gives me out just what that K value is from my F, and we can look at that later. All right, so that's the spring constant it came up with that best fit our data, about 64 newtons per meter. We also want to look at our goodness of fit. So we see here in GOF, we have a bunch of these different measurements. We have SSE, R squared, DFE, adjusted R squared, RMSE. We're only going to concentrate here on this R squared value. And we see here that it's 0.99. Like I said before, the R squared can range between 0 and 1, with 1 meaning that the curve fit the data perfectly, and 0 means it doesn't fit it at all. In this case, a 0.99 or a 99% R squared is very good. It means that our fit line fit our data very well. And then we can see under out P, we get some additional information. In this case, we're not going to be looking at too much, but that can give us more information of how this fit was done. So let's see what this actually looks like here. Now what I can do, let me remake my plot. Here, my original data, that's the data I actually measured, is the black circles here. What I can get out of this also is I can see how is this fit line going to look. So on top of this, I want to plot. I'll make new values of X. Now here I can choose whatever values I want in between the values I measured. So I'm going to go from the minimum value of X to the maximum value of X, and I'll use 100 points in between. So remember what we're doing here is we're able to kind of fill in these gaps. I only took, in this case, 16 measurements, but I'm estimating what the measurements would have been between the ones that I actually took. So what I can do is I can plot this X, big X, versus F of big X. Actually, before I do that, let's look at F again. So again, what this is telling me is F takes this one variable X. So if I say that I am looking at here 4.5 centimeters, this is estimating that the force in the spring at 4.5 centimeters would be 2.8955 newtons. Again, we didn't actually do the measurement at 4.5 centimeters, so this is that estimate. So what I'm doing here is when I make X this linear space between the smallest little x and the biggest little x I have, then what I'm going to get out of this is what that fit line looks like. And here it is in this red dashed line here. So this is the fit curve. This is what we expect the force, the relationship between the force and the deformation to be using Hooke's law from that F equals K times X. So we see that the data that we measure doesn't exactly lie on the line, but it's the best fit line that goes through our data. In this case, just a line with slope, no intercept. So how did it figure out what was the best K to use? How did it say that this was the best line to fit our data? Well, what it's trying to do, at least by default, is it's trying to make a curve, in this case a straight line, such that the distance between our actual points and the line is minimized. And we did an example like this a little bit ago when we were trying to fit a polynomial through designated points, and we wanted to see what polynomial to use. This is kind of the same idea, except here we can't put the line exactly through all of our points. So we're trying to find the one that best goes through all of our points. So we see here what we're trying to do is minimize this vertical distance between every point we have and the curve that we drew, in this case the straight line. So this is the line where if we add up all of these distances, so the distance from here to here, the distance from here to here, the distance from here to here, and we add all those up and we square them, that minimizes the sum of those squares. This is using what's called a least squares method for running the regression. And there are other methods out there, but we're just going to stick with the default, the least squares method. So any other line that we chose that had, let's say, a steeper slope, then we're missing a lot of our data points. Or if it has a shallower slope, so it's along this direction, again, it's missing a lot of our data points. So what it did is it ran through all the possibilities and it found that this slope got us closest to all of our original data. So again, to recap what we did, we loaded some empirical data that we took. We had the force in a spring at designated deformations, and we know that for a linear spring, we should obey Hooke's law where F equals kx. So we already knew what the curve should be that our data lies on. So I did a fit, and what I was trying to get out of this is, for this spring, what was the spring constant? What was that value of k? And again, we can find that after we did the fit, that the spring constant that it found that best fit our data, 64 newtons per meter.